Okay, welcome to lecture 14, and this is all about the chain rule. And this is worth writing out, the chain rule. Now, I'm going to talk about the chain rule in a couple of different ways, but first I'm going to talk about it in the functional way. The chain rule tells us how to take the derivative of composite functions, that is, functions that are built up by putting two or more functions together. So like this, when you take a function of another function. And this comes up all the time, and it's much more complicated than this because each of these functions can be very, very complicated, but you can think of them as being two things composed together, each one of which may be a bunch of other things composed together. But, the simplest example would be one that we'll do in a little while. What if f is the square root function and g is the function that takes x and squares it and adds 1? Then what would f of g of x be? Well, that would be the square root of x squared plus 1. Well, we've done this kind of thing before. We've asked questions like the domain and stuff like that. But right now we're asking a different question. What is the derivative of something like this? And see, up until now, we haven't had a way to do this. I mean, yes, we could write this as x squared plus 1 to the 1/2 power. But we haven't had a rule for telling us what to do with this. The problem is that this is not x. This in here is not x. It's not the independent variable. And so we don't have a rule. The power rule, the high school rule, does not tell us the derivative of something complicated to the 1/2. It tells us the derivative of x to the 1/2. Yeah, you can take the 1/2 down and multiply by that to the 1/2 minus 1. Yes, but not when this thing is a complicated expression. It just doesn't work. And we can try some examples of that to see it, But right now, you can take my word for it. It just doesn't work. So what does work? The answer is the chain rule. The chain rule, which tells you how to take the derivative of this thing. And what you have to do, according to the chain rule, is to take the derivative of the outer function. So in this case, yeah, you take the derivative of the outer function. So this would be 1/2 times whatever is here to the negative 1/2. And yes, you would plug in whatever is there. But the chain rule says you're not done yet. So yeah, the derivative of this thing, the derivative of f of g of x in this case, would be, sure, 1/2 times x squared plus 1 to the 1/2 minus 1, which is negative 1/2. But the chain rule says, no, you're not done. You now have to multiply that by the derivative of what's inside, g prime, the derivative of this guy. So this means you have to multiply this whole mess times the derivative of what's in there, which in this case is 2x. And that is the derivative. Now you could rewrite this, simplify it. Notice the 1/2s cancel, and you're left with x, and then this is a negative exponent, and so you could write it this way, divided by x squared plus 1 to the 1/2 power, or you could also remember that the 1/2 power is the square root. So this is actually the square root, actually the derivative of the original square root of x squared plus 1. So the chain rule says just this. In words, it says if you want to take the derivative of a composite function, a function of another function, the answer is the derivative of the outer function, plug in whatever you had, but then you got to multiply by the derivative of what's inside. Now, we might do a proof of this right now, and you might ask, well, how would you prove this? And the answer is the only thing that we have is the definition. So yeah, I would whip out the definition, the limit as h goes to 0 of this thing at x plus h minus this thing at x divided by h, and then do some kind of trick to be able to manipulate it around and eventually get to this. But I don't imagine that too many of you are interested in that. So at this point, I will say, if you want to see the proof of this chain rule, come by and see me, and I'll be glad to prove it for you, or at least give you a good argument for it. The actual proof is a little bit tricky in one little detail, but I've got a proof of it that is very convincing to anybody, any normal person. But that's not what I'm interested in doing today. Today I want to go through lots of examples of this because this is a rule that you have to know how to use. So let's look at another example. Suppose the problem is that we want to take the derivative of something like the sine of x squared. Well, the chain rule tells us exactly how to do this. This is a composite function, a function of another function. So you take the derivative of the outer function, that's going to give you the cosine, and then you plug in whatever is there. Don't change whatever is there. Okay? Notice you're not taking two derivatives at once. You're not taking the derivative of the outer function and the inner function. You're taking the derivative of the outer function, plug in the inner function, and then the chain rule comes along and says, but you got to multiply by the derivative of what's inside. So that gives you a 2x. And that's it. That's the answer. Okay? Now, many times people confuse the sine of x squared with the sine squared of x. And you've got to know that the sine squared of x is the same thing as the sine of x, quantity squared. And that's not at all the same thing as this. So what if we want the derivative of this? How do we do that? Well, the derivative of sine squared would be the derivative of this thing squared. So let's put one more bracket so you understand that it's the derivative of this thing. Now, what are the two functions here that are involved? One of them we can think of as the squaring function, the function that takes any input, not just sine of x, any input, and squares it. And then the function that's the sine x, that's what's being plugged in. So the chain rule tells us how to take the derivative of this. What's the derivative of anything squared? Well, the high school rule does tell us it's 2 times whatever you plugged in. To the first, which you don't have to write because it's not going to be there. But the chain rule now says, but you got to multiply by the derivative of what that was. If it's x, well and good, then you get 1, and that's exactly what you would expect, 2x. But this is not x, so you've got to multiply by the derivative of that, which of course is cosine of x. So the derivative of sine squared is 2 sine cosine. The derivative of sine of x quantity squared is 2 times the sine of x to the first times the cosine. Notice that's quite different from this. This is 2 times x times the cosine of x squared. Nothing like this. Okay, so don't get these functions confused. All right, another example of the power rule. What happens if you have 4x minus x squared raised to the 100th power, and you want the derivative of that? Well, the power rule, if you take anything to the 100th power, the outer function is the function that takes an x to the 100th power. So the derivative of that is going to be 100 times whatever is in there to the 99th power. And whatever is in there in this case is 4x minus x squared. Okay, that's the derivative of the outer function, plugging in whatever was there. And that's what it is. But now the chain rule says, you got to multiply by the derivative of what's inside. And that's going to be 4 minus 2x. Okay, and that's it. That's the derivative of that quantity. Let's take a look at something quite a bit more nasty. What if we want the derivative of this expression? The square root of s squared plus 1, oops, sorry, it shouldn't be the derivative with respect to x, it's the derivative with respect to s, because now I've changed independent variables. S squared plus 1 over s squared plus 4. So you ask, how do you take the derivative of something like this? Well, just look at it as a power. This is the derivative with respect to s of s squared plus 1 over s squared plus 4, all of which is raised to the 1/2 power. And now the power rule says the derivative of anything to the 1/2 is 1/2 times that anything to the 1/2 minus 1. And we've been here before. It's negative 1/2. what you have to plug in is exactly what you saw before. Don't change what's being plugged in. But then the chain rule says, aha, now you got to multiply by the derivative of what's inside. So now you have to say, well, what am I dealing with here? And this is obviously a quotient. So you have to whip out the quotient rule. The quotient rule says the denominator, the bottom, times the derivative of the numerator. So now I've got to take the derivative of s squared plus 1, but that's not hard. 2s. Minus the top part, whatever that is, s squared plus 1, times the derivative of the bottom, that's just 2s. And the whole thing is divided by the bottom squared. Okay, at this point, it sounds to me, it just feels like there's going to be a lot of stuff that's going to simplify, maybe. I can certainly pull out a 2s from here. Factoring is usually a good thing. That 1/2 is probably going to cancel with that 2, but I'll take care of that in a minute. This to the minus 1/2, well, I don't know, I'm just going to leave it. S squared plus 1 over S squared plus 4 to the minus 1/2. Now I said I was going to pull out a 2s, and what's left after I do that is S squared plus 4 minus this quantity, and the minus has to distribute. So it's going to be minus S squared minus 1, and all of that is divided by S squared plus 4 squared. Now what? Okay, I'll go ahead and cancel the 2's. So we've got S squared plus 1. You know, I'm seeing these S squared plus 4's here and here. I think I'm going to write this S squared plus 1 to the minus 1/2 up here, divided by S squared plus 4 to the minus 1/2. And then what's left? I've got an S, and inside here the S squareds are going to cancel, and I've got 4 minus 1 is 3, so I've got S times 3 divided by S squared plus 4 squared. Oops. So now, see, I think I can get rid of that. Poof. Okay. So now I'm going to combine this guy and this guy. Because they have the same base, I can add the exponents. So 2 minus 1/2 is 1 1/2 or 3/2. And the top part I'm just going to be stuck with. So we'll just say S squared plus 1 to the minus 1/2 times 3s, and this is going to be divided by S squared plus 4 to the 3/2, I said. And that's about it, really. I suppose you could put this guy back in the denominator, you could put square roots in, and the answer, if you had an answer in the back of the book for this, it might show you something like this. 3s divided by the square root of S squared plus 1 times S squared plus 4 cubed, or something ridiculous like that. Anyway, that's nothing to be afraid of. An answer like this is perfectly fine. Actually, once you cancel these guys, an answer like this would be fine. And even if there were something big that was going to cancel from here, or some major simplification, you couldn't possibly lose more than 1 point on something like that. Okay, so that's a nasty one. Let's look at one that's not quite so nasty, but maybe could cause people a little bit of difficulty. What is the derivative with respect to x of e raised to the k tangent of square root of x. Okay, now how are you going to think about this? We have to think about this as a composition of at least two functions. One of the functions is our friend e to the x, except we're not plugging in x, we're plugging in this complicated mess in place of x. But it's still basically the exponential function, it's just got another complication in it. You could think of this as a function in another way. You could call it exp for exponential, exp of x, so that this could be thought of as exp of that. So when you go to take the derivative, you can see that you're talking about the derivative of an outer function, which is really the exponential function e. And the derivative of exp is exp, because the derivative of e to the x is e to the x. Okay, well, what does that mean about the derivative of this guy? Let me get rid of the last stuff that I was writing there. Whoops, that didn't work out well. I missed. Okay, so I want the derivative of this mess. So how do I do that? The outer function is the exp function, the exponential function. What is the derivative of e to any power? And the answer is e to that power. So the derivative of e to anything is always e to that anything. So I've got k tangent of square root of x. Now I know if we did this in class at some point in the first few minutes, somebody would raise their hand and say, what's k? You know, what do you think? You know, k is a constant. You're always allowed to ask that, all right? If there's ever any doubt, you must ask, what is k? And I'll tell you, k is a constant. K does not depend on x. So as a constant, it's just going to sit there. All right, so far, what have we done? We've taken the derivative of e to a power, and the answer is e to that power. Well, not quite, because the chain rule says, oh yeah, but this thing up here is not just x. This is some complicated function of x. And so we got to multiply by the derivative. I'll write it out longhand. The derivative of what's inside. In other words, the derivative of k tangent of square root of x. You got to take the derivative of that now. So we got to write that the answer is e to the k tangent of square root of x times what? Well, what's the derivative of this thing? This is a constant times something, so the constant's just going to sit there while we take the derivative of this. What is this? This is another composite function. So we're going to take the derivative of the outer function as if we knew what we were doing. So what's the derivative of tangent? Well, we remember that. It's secant squared. The derivative of tangent is secant squared. Where? Where do we plug in? We plug in whatever's there. In this case, it's square root of x. So the derivative of the outer function, plug in what's in here, but what's in here is not just x. So you got to multiply by the derivative of what's inside. So that means we got to multiply this by the derivative of the square root of x. How do I take the derivative of the square root of x? Got to remember that square root of x is x to the 1/2. So the derivative of that is simply 1/2 times x to the 1/2 minus 1. And you might say, well, what about the chain rule? Doesn't it apply here? Well, you can if you want, but then you have to multiply by the derivative of x, which is just 1. And then you're done. There are no more variables. Okay, so this is it. This is the answer. Now you could write that x to the minus 1/2 as 1 over the square root of x if you wanted to. But there's not much that you can do to simplify this. So this one you're kind of stuck with. All right, let's do one more example that's kind of like this, really. What's the derivative of the sine of the tangent of the square root of x? It's very much like this one because we did have something of tangent of square root of x. So it's going to be very similar to this. But we can see a chain rule happening because you've got an outer function and then some messy inner function. So the answer, according to the chain rule, is, well, you just take the derivative of the outer functions. Derivative of sine is cosine. And what do you plug in? You plug in whatever's there. Just copy it over. Tangent of square root of x. now the chain rule says, got to multiply by the derivative of what's inside. The derivative of tangent of something. So the derivative of tangent of anything is secant squared of that anything. But you're not done, because now you got to take the derivative of what's inside and multiply by that. And we've been there before. 1/2 x to the minus a half. So that is it. Cosine of the tangent of the square root of x times the secant squared of the square root of x times a half times x to the negative half. And again, I don't think there's much in the way of simplification. You could rewrite it by putting the x to the minus 1/2 down in the bottom as the square root of x, but there's not much else that you can do. Okay, I mentioned at the beginning that there's another way to look at the chain rule that's not in the functional way, and this is actually a very useful way. It comes up all the time, especially in practical applications. Suppose that you've got y as a function of x, but that x itself might be a function. Couldn't x itself depend on, say, t? So if that's the case, let's think of an example. Suppose that y is the sine of x. So obviously y depends on x. But then x could be something like t squared plus 1. So x depends on t. Here's the picture that you might have in your head. Y depends on x. X depends on t. Okay? So if I make a change in t, that's going to cause a change in x. And a change in x is going to cause a change in y. So there are a lot of questions I could ask. I could ask, what's the change in y relative to a change in x? That's the question, what is dy dx? If I made a change in x, what would happen to y? How would a change in y cause a change in... how would a change in x cause a change in y? That's dy dx, nothing that you don't know already. Dy dx, in this case, would be cosine of x. But there are other questions we could ask. We could ask, of course, what's the change in x with respect to t? If I made a change in t, how would that change x? Well, that's not hard. That's just 2t. Because t here is the independent variable, and x is the dependent variable. Although x over here is the independent variable, and y is the dependent variable. We have this chain of dependencies. Y depending on x, so you can think of x as independent and determining y. But then x itself is dependent on t, so t could be thought of as independent, causing a change in x. But then, if you made a change in t, wouldn't that cause a change in y? So wouldn't it make sense to ask, what is the rate of change of y with respect to t? What would that be? Because if I change t, that will cause a chain reaction. And folks, the chain rule is called the chain rule because of this chain of dependencies and how you calculate the derivative of y with respect to something down at the bottom of the chain. So, the chain rule tells us what to do in this case, if you want to think of it in functional form, because y is a function of x, which is a function of t, so you're really looking at y equal to f of g of t, so that if you were to ask this question, what's dy dt, it's asking what is the derivative of y with respect to t, and the chain rule tells you that y prime as a function of t, dy dt, would be the derivative of the outer function, plugging in whatever's there, times the derivative of what's inside, times g prime of t. But now we have another way of writing it. Instead of writing it this way, we could say, well, what does f prime do? We already calculated f prime somewhere. I thought we did. Maybe not. Yeah, we did. Right here. dy dx. dy dx is f prime as a function of x. So f prime of g of t, remember that g of t is x. So this is, let's just do it right here. dy dt is going to be, according to the chain rule, the derivative of the outer function f prime of g of t f prime of g of t times g prime, here's where I wrote it, I couldn't find it, f prime of g of t times g prime of t. So I've already got it, and all I got to do is copy f prime of g of t. G of t is x, so f prime of x, which is cosine of x. But then we got to multiply by the derivative of what's inside here, g prime of t. And g is known to be t squared plus 1. So g prime of t, just looking at this, g prime of t would simply be 2t. So this cosine of x would be multiplied by 2t, which looks a little bit weird because you got x's and t's mixed together, and that's not usually good. So what we end up doing is substituting for x what x was equal to, and so you end up with cosine of t squared plus 1 times 2t, which is what you would have done anyway if you had seen y equals sine of x, x equals t squared plus 1. So y is really the sine of t squared plus 1. And so yes, it's pretty obvious the chain rule says the derivative of y with respect to t is going to be cosine of t squared plus 1 times 2t. Okay? It's kind of confusing to look at it all this way, and I've made it look more confusing than it is, but it isn't that bad, because if you just write it in this Leibniz form, dy dt, when y is a function of x and x is a function of t, here's what the chain rule says in the Leibniz notation. The change in y with respect to something way down here can be computed by taking the change in y with respect to the next guy down the chain times the change here, the change in y with respect to t. And this is beautiful because this chain can just go on and on. What if t in turn depends on s? And you were to ask, what's dy ds? If you were to change s, how would that cause a change in y? So the answer is, you take the change in y with respect to what y is defined in terms of, so y depends on x, measure that change and multiply that change by the change in x with respect to t, and then multiply that by the change in t with respect to s. And that's it. You just go right down the chain of dependencies. Y depending on x, x depending on t, t depending on s. The change in y with respect to s is just the product of all of these changes, all of these dependency changes. So if you think of a practical example, you think of a food chain. You know, some high-level mammal depending on something a little bit lower, which in turn depends upon something else, which in turn depends on, you know, phytoplankton or something like that. So if I were to change the phytoplankton population somehow, that would percolate all the way up the chain, causing an effect up at the top level. How fast would that change relative to a change in this low-level species? The answer is, it's the change in the top level relative to the next down, times the change in that relative to the next one down, times the change in that relative to the bottom one. Okay? And it doesn't matter how long this chain is, you can just keep multiplying by those derivatives and you'll get the right answer. Notice also that you can't mess this up because you could think of these as fractions. They're not exactly, but they behave like them. The dx's you could think of as canceling. The dt's cancel. You're left with dy ds, which makes sense. Look here, dy dt, dy dx, dx dt, the dx's cancel. You could think of it that way, although it's not, but you would be left with dy dt. So the chain rule, if you think of these guys as fractions and cancel, it gives you a truth. So if you got it wrong, you would know it. So like for instance, if you did dy dt times dx dt, you don't see anything cancel here, you know. So you'd have a dt squared on the bottom. That, you know that's bad. So this can't possibly be right. If you're using the chain rule, you're going to see cancellation happening like that. Okay, later, particularly with word problems, we'll see this kind of thing happen a lot. Okay, one last example, and that is going back to the derivative of an exponential function. But this time I want to do the derivative of 2 to the x power. Now 2 is not e, so what's the derivative of 2 to the x? I mentioned this a little bit to some of you, and I told you what the answer was, but now we're going to do it. We know the derivative of e to the x. The derivative of e to the x is e to the x. But what about 2 to the x? And we mentioned that the derivative of 2 to the x is going to be 2 to the x, except that there's going to be some kind of constant that's going to be multiplied by it. What is that? So I'm going to introduce you to a trick now, and many of you will not want to learn this trick, but I would recommend that you learn it because it's going to come in handy in just a little while. Most of you will memorize a formula for this because it's easy. It comes up a lot. But I would recommend that you will learn this trick. Here's the trick. You don't really know the derivative of 2 to a power, but you do know the derivative of e to a power, right? So just make this e to a power. Now, of course, you can't do that. That would change the problem, right? So quick, before you change the problem, make it e to the log of 2 to the x. Okay, now before you do anything else, does anyone doubt that these are equal? I mean, e and log composed with each other cancel, so e to the log of anything just gives you that anything. So I've got 2 to the x on the right that I'm taking the derivative of, just like I did over there. I have not changed the problem. Okay? But notice that when you have log of an exponential expression, this is the same as e to the what power? This x here is going to come out of the log, right, as a multiplier. So I'm going to get x times natural log of 2. So this is now my exponent, e to that power. And we know the derivative of e to any power. The derivative of e to any power is e to that power again, e times x ln of 2. Except the chain rule has something to say. Chain rule says, oh yeah, but you got to multiply by the derivative of what's up there, what's inside the exponential function. What's inside here is not x, it's some complicated function. So the derivative of e to that power is e to that power again, times the derivative of what's inside. So what's the derivative of what's inside here? Well, it looks like it's a product. Would you use the product rule? I wouldn't, because I'd look at this thing and say, wait a minute, what's natural log of 2? What kind of a thing is natural log of 2? Answer, it's a constant. It's something you could put on your calculator. So if I want the derivative of a constant times x, that's easy. It's just the constant. So the derivative of this, the derivative of e to the x ln of 2 is e to the x ln of 2 right back at you, times the derivative of what's inside, which is just log of 2. And there's one more thing I can do with this. I can back this out. In other words, pull this x back inside the log now that I've done this. So this is now e to the log of 2 to the x times log 2. So the x could be pulled out for a moment and then brought back in again when we're done with it. So here I am with e to the log of 2 to the x again, which of course I could cancel. And here's my final answer. E and log cancel, and I've got 2 to the x times the natural log of 2. So yes, the derivative of 10 to the x is going to be 10 to the x times the natural log of 10. The derivative of 42 to the x is going to be 42 to the x times the natural log of 42. So yes, you can memorize that, but you might wonder what would happen if you were trying to take the derivative of, how about x to the x power? We're going to look at that in a little while, but not today. The problem is the answer to this is certainly not x to the x times natural log of x. It's not quite that simple, nor is it x times x to the x minus 1, the power rule. No. Neither is the derivative of 2 to the x times 2 to the x minus 1. No, you will be crucified if you write that kind of thing. This is an exponential function. It does not behave according to the power rule. So the derivative of an exponential function is always an exponential function times something. In the case of a constant base, it's just the natural log of the base. In case of something more complicated, well, you're going to have to use this trick of writing x to the x as e to the log of x to the x, and then go from there. But as I said, that's for another day. Okay, we've all suffered enough. You now know enough to be able to do the problems, although we're going to take them in 2 days so that we have a chance to have at least a couple of quizzes and some feedback about how to do some of the more complicated examples.